So previously we talked just now, if let's say the sectioning itself, we're sectioning is perpendicular to the specimen itself. But if let's say we're making an angle, okay, we're making a particular angle. So what is happening here is that actually is that our normal and shear force will also act at a particular angle. Okay, so here this is how it look like. Okay, so we look like this. Okay, so your normal force would act like this, would act perpendicular to the surface itself. Your shear force will act along the surface itself. Okay, and your bending moment will also act along the surface itself. Okay, and basically the same also will go for the other side. Okay, let me add your friend first. Okay, okay, so the same also will go for the other side also. Okay, because let's say we section it from the other side a particular angle, then this also will happen. Okay, this will also happen as well. Okay, so we need to say that your normal force, okay, will act normal to the surface. Your shear force will act along the surface, and your bending moment will also act along the surface as well. Okay, and basically the angle that they're acting to, okay, the angle that they're acting to actually is this. Let's say for a normal force, this particular angle that they're acting to is the same as this angle alpha. Okay, your shear force also is acting at this angle as well. If you use your trigonometry, it's like acting to alpha. And the thing about bending moment, guys, is that the bending moment, regardless of how you section it, whether you section it with an angle alpha or whether you section it 90 degrees, it will still be the same. Okay, it is not affected at all. So I would say this is not affected by alpha. Okay, not affected by alpha at all. Okay, however you section it is not affected, because the thing about movement, guys, is that movement itself is just the turning effect of the body. Okay, it causes the body itself to turn. Okay, so we need to say, like, if you have a body, so movement itself, what the bending moment does is that it just causes the body to turn. It causes this particular section to orient itself. Okay, so you don't have to worry about the bending moment. Actually, you will not be affected by alpha, but your normal force, your shear force, is affected by alpha. Okay, so okay, okay, hold on. Yeah, guys, I think a lot of you guys are joining. Okay, so it's affected by alpha. Okay, so therefore this is quite important to actually take note. Now, I think maybe you guys probably are a little bit confused, like what am I talking about? So let me do this tutorial with you guys. Okay, I think I will do the tutorial with you guys, and then we can see the answers that I've done. You guys can follow along with me as well, and we'll be able to, how do I say, we'll be able to understand this kind of question better, because this kind of question sometimes they can give in your final exam. This one actually I took from the past year paper, if I'm not mistaken. Okay, so let's go and solve this together. All right, we're gonna solve this part together. So I suggest you guys also to take out your notebook and everything. Just write what I'm write as well. Like, just try to take notes of what I'm doing or how I'm doing it, so that you guys also later can watch the video and also try to understand. Like, if let's say something you're confused about for this particular example. So going back to our example, where is it? Okay, yeah, this example, right? Okay, so let's say we have this particular object. Okay, we have this particular beam, for example. Okay, we have this particular beam, and we're applying a force, okay, which I'll mark in white color. This force is 2000 newtons. Okay, this force is 2000 newtons. Okay, and okay, 2000 newtons. We're applying a force horizontally, yeah, horizontally. And I think for the normal case, right, I think let's say we section it normally. Okay, we section it normally. Let's say I call this section AA. I cut it half normally, perpendicularly 90 degrees. I think you guys can easily find the internal forces, right? You can easily find the, in this case we're interested in finding only the normal and shear forces. We're only interested in these two. Okay, what is the normal force and the shear force? Okay, so for AA, I think I leave it to you guys. You guys can easily find a normal and shear force, but we're more interested in section BB. Okay, for example, the one that we saw in the tutorial. Okay, and I will choose the angle to be 60 degrees. I know the example here said 30 degrees, but once I do this particular angle 60 degrees, later when you try back again, then you guys can also you know, do it will be the same answer. It will be a similar method. Okay, clear guys? Okay.
Yes, sir.
Okay, great. So please follow along. Okay, this is quite important. So we're gonna be only doing for BB right now. Okay, for AA I leave it to you guys to do it. Okay, so let's say for section BB, how do we do this? Okay, first and foremost, we take the sectioning at BB. Okay, so I will draw the sectioning at BB itself. Okay, just take a very simple 3D sketch of it. Okay, and then okay, all right. Okay, so we know here is 2000 Newton. Okay, we know here is 2000 Newton. Now, our normal force actually at BB, sorry, at section BB, I took the left side. You take the right side also no problem. Any side will do for this case. It's acting, okay, how do I say this? It's acting actually in perpendicular to the, I would say it's perpendicular to the surface, okay? Normal force, okay, by definition, so you have to remember the normal force, okay, why is it called normal? Usually will act perpendicular to the surface. Will act perpendicular to the surface. Okay, you'll act perpendicular to the surface. Okay, shear force, okay, shear force on the other hand will act parallel to the surface, parallel to the surface. Okay, so your shear force for this case for BB will act parallel to the surface, since we know that the convention is going downwards. If you take the left hand side, the shear force convention is going downwards. If you take the right side, you know the shear force will be going upwards. Okay, but we're taking the left side because I think it's, you know, it's easier to look at it that way, but again, it's not a problem whichever side you take. So this is VB. Okay, so how are you going to find the VB and how are you going to find the NB in this case? Okay, here's the tip. We know that is 60 degrees. Okay, once we section it, we cut it like as if, let's say you take a sword and cut it in 60 degrees from the normal, the perpendicular line basically. Okay, so that means that the orientation, okay, from the normal axis to this point is what? This is basically horizontal. Yeah, perfectly horizontal. This is 60 degrees. Okay, and from here, okay, from vertical, if you take the vertical side, it is 60 degrees. Okay, it's 60 degrees. Okay, and I forgot to mention, but the bending moment also does exist, because whenever you section, right, you also have to consider the bending moment. But why I didn't draw the bending moment is because this is not our interest. We want to find normal force and we want to find the shear force. Okay, so that's why the bending moment is of no interest to us actually. Okay, that's why I leave it as it is. So now, how we find the normal force and how do we find the shear force? Very simple. You use your equation of equilibrium, okay? Meaning to say that your equation of equilibrium, okay, is what? Summation of fx equals 0 and summation of fy equals 0, okay? And we don't have to worry about the moment case. Why we don't have to worry about moment? Because we're not interested in it, okay? when summation fx equals to 0, okay, what does it mean? So we take, if we were to consider the direction of the x and y axis, where x is positive, y is positive going upward, x positive going to the right, so we can say that NB cosine 60, okay, because the cosine 60 is obviously going to go in the positive direction, right? The cosine 60 here would go in the positive direction, right? Okay, if you cosine 60, NB cos 60. And for VB, okay, we have the sine 60, okay, meaning to say that if we do the sine of 60, okay, your friend wants to join, okay, because cosine 60 is going vertical, but if you do the sine 60, it is going to go, it's going to go that way, okay. This is VB sine 60, okay, VB sine 60, okay. So sine 60 is going that way, going the negative side. So you're going the negative side, so it becomes minus VB sine 60 degrees. Okay? And we know this 2000 Newton force is also going to the left, so it becomes minus 2000 equals to 0. Sorry, put equal to 0 here, okay? So we're left with what? So we have cosine 60, so cosine 60 on the calculator should give you, oh, okay, hold on, yeah, give me a minute. Unit, degree, cosine 60. Okay. Cosine 60 will give you half NB. Minus sine 60 will give you what? Sine 60 will give you square root 3 over 2. Okay? VB equals to 2000. Okay, so I'm going to move the 2000 to the 0 side, become positive. Okay? So this is your first simultaneous equation. So I will erase this. Is it okay if I erase this one? Oh, sorry. Is it okay if I erase this part, guys?
Yes.
Okay. So I erase this off. So now, we're going to find for Fy equals to 0. So for Fy, in this case, how we're going to find our Fy? Our Fy only, there's only related to NB and to VB itself. Okay? So it's really related to NB and VB itself. So in this case, NB, if it's making a y component, it's going to go downwards here, which would be NB sine 60 degrees. And for VB, if it goes to the negative y component, it becomes what? Becomes VB cosine 60 degrees, also going downwards, right? So it becomes negative. So in this case, it becomes minus NB, I'll write it here actually, minus NB sine 60 minus VB cosine 60 is equals to 0. And then you rearrange the equation. We know that cosine 60 is half, right? So cosine 60 is obviously half. So it becomes half VB equals to negative sine 60 becomes what? Square root 3 over 2 NB. Okay, I'm gonna move you guys here. Okay, becomes NB, right? So this is if you rearrange your equation also, you can say that VB is equals to what? If I rearrange the equation, VB equals to negative square root 3 over 2 divided by half. So it becomes negative square root 3 NB. Okay, so this is your equation number 2. So you have two equations. One equation is right here, another equation right here, right? So what you can do to solve this problem, guys, you can substitute this equation 2 into equation 1. So I'm going to substitute right away. So it becomes 1 over 2 NB minus square root 3 over 2 times negative square root 3 NB equals 2000. Okay, equals to 2000. So what we have here, 1 over 2 minus root 3 over 2 minus root 3 2. Okay, so it becomes 2, right? So then we have here 2 NB equals to 2000. So your NB, your normal force is just 1000 newtons. Okay, and now for your shear force, it is just negative root 3 times 1000. Okay, which would give you what? So negative, so root 3 times 1000. Okay, so I'll give you negative 1732 newtons. Okay, negative here actually meaning to say that this negative means that the direction may be going upwards. Okay, the direction for VB is assumed wrong. It will be going upwards in this case, which is no problem, by the way, don't worry. Okay, so negative means that VB actually supposed to be going here. So this negative means that it's actually supposed to be going upwards. Okay, because we assumed that VB was going downwards initially, but our assumption for the direction of NB is correct. It is actually going sorry, it's actually going in this direction, so no problem at all. Okay, so is it clear actually how we found our VB, how we found our NB for this case, guys? Is it clear so far?
Yes.
Okay, so
Yes, sir.
similarly, I think I will leave you to this question. Obviously, now this question they use 30 degrees, but the same rules still apply. Okay, for solving this kind of problem. So I will leave it to you guys. Actually, the answers also are included as well. So you can see, this is basically, if let's say you're doing the normal case, user section, it becomes very straightforward. VA is equals to 0, obviously. NA equals to 2000, okay? But for tutorial 2, as you've seen, what I've done earlier with the 60 degrees is the same concept, same method also. Okay? So, yeah. So that's about it for the tutorial session. Okay, and I also left you guys with 2 supplementary questions with the answer as well. Okay, and yeah, this supplementary question 1, supplementary question 2, it's about frames and machines. Okay, and I know it looks a bit tricky at first when you're looking at this kind of question. You're probably like wondering, okay, how do we do this question actually? How do we solve this question? So, determine the magnitude of the reactive force at pin A and the short link BC. Okay. So, first thing is to find the magnitude of the reactive force at pin A and the short link BC. So, how do we do this? We draw the free body diagram for the components. So, first, for example, you draw the free body diagram for this one. Okay. So, at BC, you see it's a link, right? So, meaning to say that it's just going to be only one force. Okay, just one force only, because BC is a two force member. Okay, how do you know BC is a two force member? Because it says a link and there's only like 2 pins here, right? So you can say that they're just simply a two force member. Okay, because it's acting on 2 points only. The force at B and C are acting on 2 points, so therefore it's a two force member. Okay, so just keep in mind, once you draw the free body diagram for this handle, this is gonna go downwards lah, basically. And for A, it's a pin, so it's a pin, so therefore don't forget to consider the AX and the AY. Okay, then you can find the reactive force of the pin itself, and the short link at BC is just simply going downwards because it's a two force member. You can simplify it as it is. Alright, and once you do that, you use the equation of equilibrium, right? Summation of fx equals to 0, summation of fy equals to 0, and then summation of moment, at which point you want to take the moment. I suggest you take the moment at point A, okay, equals to 0, okay? Of course, remember to put your correct rotations, okay? So clockwise is 0, okay? And then you can easily solve for AY, AX, and FBC. So once you are done solving for AX, AY, FBC, then they ask you to find the internal resultant loadings acting on the cross section at D. So they want you to find it here. So how do you do it? So my advice is, if let's say you section at D, right? You section at D. Which is the easiest to do? Which is the easiest to solve the problem, guys? Is it taking it at this side? You want to do it at this side, the right side, or you want to do it at the left side? You want to take it at the left side. Okay, so which one you guys want to do it? I leave you guys to think about it, obviously, because if I tell you the answer, it'll be it'll be a little bit obvious. But I always say take the one with the least number of external loadings. Okay, remember the key point, least number of external loadings. Least number of external loadings. Okay, because it will give you the less headache. So you can see which side is the least number of external loading, whether it's the left side or whether it's the right side. When you section at D, then you do the least number of, once you follow this tip, then you can find the internal loadings, meaning to say the shear force at D, the normal force at D, and the bending moment right at section D. Okay, so I leave you guys to determine which one is the easier one and solving the problem. I've already given you the tips already, and of course the answers are here as well, so you can cross check if you got the correct answers or not. Okay, and yeah, that's about it actually for this chapter. So any questions so far about chapter 7? Any issues so far? Okay,
So
so
far, okay, sir.
okay, good. Okay, so I'm assuming there is no issues so far. I'm gonna stop